Okay, today we are going to learn some more tests to determine whether a series converges or diverges. So we are working out of two sections from our book today, and the tests that we are going to learn are called the direct comparison test, the limit comparison test, the ratio test, and the root test. The direct comparison test is the first one we're going to take a look at. This will not work in any situation. If you have two series where one is smaller than the other, so when I say one is smaller, I'm talking about the magnitude of the terms of one series. Each term, term by term, is less than the other. So if you can't determine which one is smaller, then you can't use this test. But if you have identified one that is smaller than the other, there are two things that would be true. If the bigger series converges, the smaller series must also converge. And if the smaller series diverges, the bigger will also diverge. If you have the other scenarios where the bigger series diverges or the smaller one is converging, this test is completely useless to you. Some helpful things to know. First, constant terms in the denominator can be deleted without affecting convergence or divergence. Secondly, if you have a polynomial in the numerator and or the denominator of a sum, all but the leading term can be deleted without affecting convergence or divergence. These are some things that you would want to do to create your comparison series. You can't just do those things and assume that your series will behave the same way unless you use your direct comparison test. So you're going to have to show some work to do this, and I'm going to give you some examples where we will see what that looks like. You might want to pause the video now to take the time to finish writing down this slide worth of notes, and then we will work an example problem on this together. Okay, so for our first example, we are going to take a look at the sum from k equals 1 to infinity of the series 1 divided by the square root of k minus 1/2. So for a comparison test situation, you're not going to be given the series that you compare it to. You create the series that you compare it to by thinking about those helpful things that you wrote down just the last slide. So we have a constant term in the denominator, that negative 1/2. So if I delete that, I can say, well, this series behaves like the series from k equals 1 to infinity of 1 over the square root of k, for the reason that we know deleting a constant term in the denominator won't affect convergence or divergence. So these two series, we could compare them. So what do we know about this one? Well, this series is equivalent to 1 over k to the 1/2 power, the sum from k equals 1 to infinity of 1 over k to the 1/2 power. And we learned about this type of series last time. This is called a p-series, and we know that since p is less than or equal to 1, this series diverges. So now the next bit of work to be done on a comparison test, other than choosing a series that you're going to compare it to and looking at how that one behaves, is figuring out which one is smaller. A good idea is to try substituting a 1 in to determine the first term in both series. However, I'm going to tell you there are some cases, and you may see this in your assignment, where the series starts with one that is larger than the other, but then they switch places. So you may need to check a few terms out to be sure, okay? But for these particular series, if I substitute a 1 into the first one, I get 1 divided by the square root of 1, which is 1, minus 1/2. 1 divided by negative 1/2 is 1 times negative 2, so that one gives me a negative 2. Then the other series is 1 over the square root of 1, which is just 1. So the series 1 over the square root of k is smaller than the series 1 over the square root of k minus 1/2. You can also think about it like if you're subtracting something in the denominator, you're making that denominator larger, and if you think of, you're making it smaller, so a smaller denominator would make the overall value of the fraction larger, like 1/2 has a smaller denominator than 1/3, but 1/2 is a greater quantity than 1/3. So your next step in your comparison series is to state which one is smaller than the other. So we're going to state for this one, the sum from k equals 1 to infinity of 1 over the square root of k is less than or equal to the sum from k equals 1 to infinity of 1 over the square root of k minus 1/2. Okay, so in red here, I've tried to show the work that I was kind of saying mentally, but I think I said that it was a negative 2 for the first term on this first series 1 over the square root of k minus 1/2, because I was thinking about subbing a 0 in for k, but you start with k equals 1, so plugging in a 1 would give you a first term of 2. And plugging in a 1 to 1 over the square root of k gives you a first term of 1. So the greater series is the one that we listed first. So we're going to write that inequality to start. In order to use the direct comparison test for convergence, you must always state which series is smaller or larger than the other one to use it. So we now know that this smaller series, 1 over the square root of k, this one is the smaller, is diverging. So since the smaller series diverges, the smaller series diverges, therefore the larger series, which was the one we started with, also diverges by the direct comparison test. So as a review, for a problem like this, the first step is to come up with a series to compare it to by using those helpful hints from before. Look at that series' behavior. State which one is larger and smaller than the other with an inequality statement. And then hopefully it fits into one of those two cases that the bigger series is converging or the smaller series is diverging, so that you can state the behavior of your given series. If not, this test will not be helpful for you. All right, let's try another one of these. Example 2. We're going to look at the sum from n equals 1 to infinity of 1 over 2n squared plus n. So we want to figure out a series that we could compare this to. in our first example, we had a constant term that we were able to delete without affecting convergence or divergence. This one doesn't have a constant term in the denominator. So our other helpful thing to think about is that if you have a polynomial in the numerator and or the denominator of the sum, all but the leading term can be deleted without affecting convergence or divergence. The leading term would be the one with the highest power of your variable. So we're going to say that this one compares to the sum from n equals 1 to infinity of 1 over 2n squared. Okay? Now, this looks pretty close to a p-series, but it's not exactly a p-series because it's got a 1/2 multiplied by it. We can pull that 1/2 scalar multiple out in front of the summation and say n equals 1 to infinity, the sum from n equals 1 to infinity of 1 over n squared. So we're going to compare it to this, which we know is a p-series. P is equal to 2, which means p is greater than 1. And if p is greater than 1, the p-series converges. Okay, so we've looked at the behavior of our comparison series. Now we need to determine which one is smaller. So we're going to substitute in values to determine that. We want to substitute values into like the original comparison series, this one right here, 1 over 2 times n squared, rather than the one where we pulled the 1/2 out in front. That was just to determine whether that one converged or diverged. So let's substitute in a 1. 1 over, I usually do this in my head, not written down, but I've decided to write it down just to make it a little more clear for y'all. 1 over 2 times the quantity 1 squared plus 1 would equal 1 over 2 plus 1 is 3. So our first term here is 1/3. If I go to my other one, 1 over 2 times 1 squared equals 1/2. So for our first terms, which one has a larger first term? Our comparison series has a larger first term. You can generate out another term if you'd like to. 1 over 2 times 2 squared plus 1 equals 1 over 4 times 2 is 8 plus 1 more gives us 9. So the second term is 1/9 over here. Then for our other series, 1 over 2 times 2 squared would equal 1 over 2 squared is 4 times 2 is 8. Keep in mind, a smaller denominator on a fraction means the overall value of the fraction is greater. 1/2 is bigger than 1/3. An 1/8 is bigger than 1/9. Because we have this plus n on the first original series, that makes the denominator a little bit bigger on that one, which reduces the value of the overall fraction. So you may be able to figure out which one is greater without even substituting in numbers if you just think of your number sense, what is going to happen to the value of that fraction as I increase the denominator a little bit more than the other. That one will be smaller. So now we're going to write an inequality statement. I always start with the smaller one and then write less than or equal to. The sum from n equals 1 to infinity of, my smaller one is the original, 1 over 2n squared plus n is less than or equal to the sum from n equals 1 to infinity of our comparison series, 1 over 2n squared. So, because the larger series is converging, our bigger series is the one we compared it to, it is converging. The smaller series must also converge by the direct comparison test. So the larger series converges, therefore the smaller series also converges by the direct comparison test. Okay, our next test is very similar to the direct comparison test in that we will compare one series to another, but we don't have to look at which one is larger or smaller on this one. The limit comparison test states that if the limit as n approaches infinity of a sub n divided by b sub n equals L, and L is finite and positive, finite meaning not infinite, positive meaning not negative or zero, the series will both converge or both diverge. They will have the same behavior as each other. We're going to start looking at this test with example 3. It's going to be exactly the same as example 2. This is not a mistake. I want you to be able to compare the two comparison tests. So we're going to do the same series again. So we already know the answer, but we're going to look at how do we get that using a different method. The series from n equals 1 to infinity of 1 over 2n squared plus n compares to the series from n equals 1 to infinity of 1 over 2n squared. We deleted the plus n on that polynomial. We know that series would be the same as 1/2 times the series from n equals 1 to infinity of 1 over n squared. This is a p series. Our p is greater than 1 and it converges. Okay, so that's all work that we did the same on example 2, but now we're going to do our limit comparison test. So we write the limit as n approaches infinity of the original series. A sub n is your original series, so 1 over 2n squared plus n divided by b sub n. B sub n is our comparison series right here, circled in red. So if I divide by that fraction, I'm going to multiply by the reciprocal of that fraction, which would be 2n squared over 1. So this is equal to the limit as n approaches infinity of 2n squared divided by 2n squared plus n. And what do we know about this function? This is a rational function. The degree of the numerator and the degree of the denominator are the same, which means it has a horizontal asymptote at the ratio of the leading coefficients. So if I take those leading coefficients, 2 over 2, and simplify, that equals 1, and that would be the limit as n approaches infinity. Since that limit is both positive and finite, since the limit is positive and finite, the series will have the same behavior. Our comparison series converges, so that means the original converges also. So we can say the series both converge by the limit comparison test. All right, let's try another example using our limit comparison test. Okay, for example 4, we're going to do this one using the limit comparison test as well. We're going to start with the series from k equals 1 to infinity of 1 over the square root of k plus 1. We need to compare that to another series. Can you imagine what we're going to compare it to? How about the series from k equals 1 to infinity of 1 over the square root of k. Take off that plus 1. This is a p series because the power on the k is 1/2. So the p is less than or equal to 1, which means this series is diverging. So now we're going to figure out what's going on with our original by doing the limit comparison. The limit as k approaches infinity of the original series, 1 over the square root of k plus 1. We're going to divide by the comparison series, which means we're going to multiply by the reciprocal of the comparison series. And that is going to equal the limit as k approaches infinity of the square root of k divided by the square root of k plus 1. The degree of the numerator and the denominator are the same, so that means there's a horizontal asymptote at the ratio of the leading coefficients. So that's going to be 1 over 1, which equals 1. Since the limit is finite and positive, the series will have the same behavior. So the series diverges, because we figured out our comparison series diverges by the limit comparison test. Okay. Okay, next we're going to learn about the ratio test. To do the ratio test, which is a very versatile test and can be used on lots of different kinds of series, you're going to figure out what L is. It's going to be a limit as n approaches infinity of a sub n plus 1 divided by a sub n. So I'll show you how we work that out. Once you get that limit, you're going to look at it and analyze it. If your limit is less than 1, the series converges. If your limit is greater than 1 or equal to infinity, the series diverges. If L is exactly equal to 1, the series might converge or might diverge, so you're going to have to try another test, which is a bummer. So we're going to do example 5. This one is the sum from k equals 1 to infinity of k to the k power over k factorial. Y'all remember factorials? When you multiply a number times every integer preceding it down to 1. Alright, so we're going to figure out what this number L is. L is going to be equal to the limit as k approaches infinity of k, well, we're going to plug in k plus 1 everywhere we see a k in this series. So it's going to be k plus 1 raised to the k plus 1 power divided by k plus 1 factorial. So to create that a sub n plus 1, it's the same thing as your original series, except for everywhere the k was, we're going to fill in a k plus 1. Then we're going to divide it by the original series or multiply it by the reciprocal of the original series, k factorial over k to the k power. Now, the next thing to do is all algebra. This is not calculus. This is simplifying with algebra. So we're going to make it a little bit easier. I want you to think, before I start working here, about an algebra rule you had. If you had x to the 5th times x to the 2nd, you would get x to the 5 plus 2 or 7th power. So do you see how we have addition in the power? I want to split that into two separate bases, k plus 1 raised to the k power times k plus 1 raised to the 1st power. and then I'm going to multiply that by k factorial, all divided by k plus 1 factorial would mean k plus 1 times the number that came before it. What is one number less than k plus 1? I guess that would be k. So it would be multiplied times k factorial, all the numbers that come before k, we don't know how far that goes, all the way down to 1. So k plus 1 factorial simplifies to k plus 1 times k factorial. Then we're going to multiply that times k to the k power. So we're going to have some things that are able to cancel out now. K plus 1 on top divides out with k plus 1 on the bottom. This is great. This is nice. This is good. K factorial divides out with the k factorial on the bottom. So now we're looking at the limit as k approaches infinity of the quantity k plus 1 to the k power divided by k to the k power. Since those have the same power, they can be put together as one fraction, all to the k power, which would mean the limit as k approaches infinity of k plus 1 over k raised to the k power. And that fraction in the parentheses can be split into two fractions. It's kind of like the reverse of finding a common denominator and putting something together. You're breaking it into two fractions with that same denominator. So it'd be k over k plus 1 over k raised to the k power. And that simplifies just a little bit the limit as k approaches infinity of 1 plus 1 over k to the k power. Now, those of you who've been studying your note cards, you know what this is equal to because it's in your note card stack. And it's in there for a reason. So, the limit is equal to e. This was something we learned in the very first unit of the year. What do you know about the number e? This is the answer to the limit problem. Is it less than 1? Is it greater than 1? Is it equal to infinity or is it equal to 1? Well, e is a number that is greater than 1. And if it's greater than 1, what do we know about this series? This series must be diverging. It diverges by the ratio test. Okay. Let's go on to example 6. We're going to look at the sum from k equals 1 to infinity of 1 over 2k minus 1. So we're doing this again, practicing using our ratio test. So we're going to look at the limit as k approaches infinity of our original series with k plus 1 plugged in where the k is. So 1 over 2 times the quantity k plus 1 minus 1. And then we divide that by the original series, which means we multiply it by the reciprocal of the original series. So we'll say this is the limit as k approaches infinity of 2k minus 1 over, let's go ahead and distribute that to 2k plus 2, then minus 1 would be plus 1. Okay, so what's that going to give us? We have a rational function. The degree of the numerator is the same as the degree of the denominator, so the limit would be the horizontal asymptote, the ratio of the leading coefficients, 2 over 2, which equals 1. What did we say happens when the limit is equal to 1 on the ratio test? Unfortunately, this is the case where the ratio test is completely worthless, so we must try another test. What test do you want to try? Well, looking at it, to me, it looks kind of close to a 1/2k situation, deleting that -1. So I want to do the comparison test. You could do direct comparison or limit comparison. I think I don't want to worry about which one's bigger or smaller. Let's just try the limit comparison. Let's get some more practice with the limit comparison test. Let's give that one a try. So how does that work? We have to compare it with another series. So the sum from k equals 1 to infinity of 1/2k minus 1 would compare with the sum from k equals 1 to infinity of 1/2k. You could pull that 1/2 out in front and say 1/2 times the series from k equals 1 to infinity of 1/k. And what do we know about that series? That's a special series. That's the harmonic series. And what do we know about the harmonic series? Does it converge or diverge? It diverges. So now we're going to do the limit as k approaches infinity of our original series 1/2k minus 1 divided by our comparison series, which means multiplied by the reciprocal of our comparison series. And now we will work out that limit. The limit as k approaches infinity of 2k over 2k minus 1. Oh, the degree of the top and the bottom are the same, so that's just 2/2, which is 1. And since the limit is finite and positive, both series will do the same thing. Both series diverge by the limit comparison test. All right, our final test for today's lesson is called the root test. You are again going to calculate a limit equal to L. That limit will be the limit as n approaches infinity of the nth root of the absolute value of a sub n, which is your series rule. And that's going to equal the same thing as a sub n raised to the 1/n power. So sometimes it's helpful to have it as a root, sometimes as a power. If that limit is less than 1, we're going to say that the series is converging. If the limit is greater than 1, which includes infinity, then it's a diverging series. And if the limit is equal to 1, the test fails. So let's try an example of this. Example 7, we're going to do the sum from k equals 2 to infinity of the quantity 4k minus 5 over 2k plus 1, all raised to the k power. So we're going to do the limit as k approaches infinity of this series rule under the kth root. So we've got to the k power, then we're going to take the k root. That's nice because the k root cancels out the k. So now we're just looking at the limit as k approaches infinity of 4k minus 5 divided by 2k plus 1. Rational function, same degree on top and bottom. So the horizontal asymptote would be the ratio of the leading coefficients, 4/2. 4 divided by 2 is 2. 2 is a number that is greater than 1, which means, therefore, the series diverges by the root test. So this is a kind of nice, easy test. All right, this is our last example, number 10. Another root test problem. It is the sum from k equals 1 to infinity of 1 divided by the quantity natural log of k plus 1 all raised to the k power. So we're going to do the limit as k approaches infinity, and I'm going to take the kth root of 1 over the quantity natural log of k plus 1 raised to the k power. Well, the kth root of 1 is 1, and then the kth root will cancel with the k on the bottom, so this is going to be the limit as k approaches infinity of 1 over the natural log of k plus 1. If we send k to infinity and we look at the right-hand end behavior of this function in the denominator, infinity plus 1 is infinity, the natural log of infinity is going towards infinity, and 1 divided by infinity is 0. So this limit is equal to 0. That number happens to be less than 1. Therefore, the series converges by the root test. Yay! Good job, class. So, your homework assignment is out of the textbook. Practice, practice, practice. And I will see you next time. Have a great day. Bye. Oops, I just turned off the video and then looked down at my notes and noticed this was not example 10. This was example 8. So, sorry about that. Bye.